As I said, thank you very much for that kind introduction. This session is partly about updating everyone on the activities we've been doing at the IOWC in the last year, or at least some of the ones that I've been doing in conjunction with some of my colleagues here. It's going to teach some of the methods and ideas that we've been using. And I'm going to ask you to use these ideas as well in a kind of workshop setting in breakout rooms. Then we'll come back at the end to discuss them, discuss your findings, discuss the methodological challenges you faced as you did that. Most of you here are related in some way to the Appraising Risk project, which Professor Campbell kindly just introduced, either through being a co-applicant, a collaborator, a postdoc, or student whose position is at least partly funded by funds on the project. I also know that I think we have a couple of visitors from outside. Everybody is, of course, welcome. I'm going to try and make this as accessible to all as possible. So we're going to kind of begin with a little bit of a refresher on some of the core aims of the project, with a view to detailing the rationale for the subject matter of this session. So as Professor Campbell indicated, the full title of this project is Appraising Risk, Past and Present. Interrogating historical data to enhance understanding of environmental crises in the Indian Ocean world. It is a well-known scientific fact that the fate of humanity is endangered by present-day global warming, but the specific ways in which it is so are still very much under investigation. Climatologists are still very much in the process of understanding world climatic systems and the different ways they are affected by changing global temperatures. Meanwhile, social scientists and scholars of the humanities are at an even earlier stage of documenting how humans have adapted in the face of past climatic changes. And this kind of idea of adaptation and building resilience over time is going to be more focused on in Professor Chris Lowe's presentation or session in the second part of this workshop. The models that climatologists develop and use to model future changes in climatic systems generally, though not exclusively, generally are limited by the time depth of their data. A lot of them are reliant solely on data from the 20th century and after. And this is partly because of the availability of data. From this point, around the beginning of the 20th century, we have available several measured records in quantitative form, things like from rain gauges, barometers, and thermometers. And then from mid-century, we can add satellite data as well. But there is data from the deeper past, which this project seeks to interrogate or to uncover first and then interrogate. And this is very much where this session of the workshop comes in. It is about accessing and interpreting data from the deeper past and making it interoperable then with more recent statistical data to make a long-term time series that starts from before when statistical records were abundant and continues through that statistical period. For this purpose, we're going to focus on rainfall. This is for two reasons. One is because I'm shamelessly promoting my own research and expertise. Some of you may be aware that I have an edited volume coming out next month, Droughts, Floods and Global Climatic Anomalies in the Indian Ocean World, which I've contributed a chapter to, but also several members of the partnership have contributed chapters to as well. And if you are taken by the subject of this session, I urge you to give it a look. I hope your libraries will pick it up. But the main reason really is that I hope everyone here has in some way an interest in rainfall in the Indian Ocean world. And if you don't have an interest in it, I'm going to kind of make the case as to why you should. Now, the Indian Ocean world studies really became kind of close to mainstream, picking up steam in the 1980s. And at that time, kind of the Indian Ocean world was sort of defined by the Indian Ocean monsoon system was seen as absolutely integral to the understanding of the Indian Ocean world. But it's done so mostly in terms of winds and currents, which allowed sail-powered trade around the Indian Ocean world. And trade begat cultural exchange over large areas. And this is kind of very much the kind of early focus of Indian Ocean world studies, Indian Ocean world history, on human connections, facilitated by the monsoon system. this project, kind of building on that, but also modifying it as well, kind of defines the focus on another aspect of the Indian Ocean monsoon system, and that is rainfall. The monsoon system brings rainfall to every part of the Indian Ocean world. And we can define the Indian Ocean world as the region or the macro region in which communities or agriculture is reliant on rainfall being brought by the Indian Ocean monsoon system. This includes regions as distant as northern China and Egypt, not just the regions that actually border the Indian Ocean world. For Egypt, the latter's rainfall regime is dependent on the agricultural system is dependent on the annual flood of the Nile River, which is partly fed by regions in Eastern Africa, for example, Ethiopia and Uganda, bringing Indian Ocean monsoon-related rainfall. So, if we're focusing on rainfall, what form does rainfall data come in? And here's just a kind of example, just going to kind of as a prelude to what we're going to discuss in more depth moving forwards. On the left, on this slide, we have the rainfall measurements taken from a rain gauge in Dodoma here, which is the capital of Tanzania. And these are the 4 wettest months on average per year, December to March. And December, there's 117.5 millimeters. In January, there are 43.5 millimeters. In February, there's 57.5 millimeters. And in March, there's 135.7 millimeters of rainfall. Pretty precise measurements. The total for these 4 months was 354.2 millimeters. And this represents 74% of average. The average is 477 millimeters for these 4 months. And this deficit contributed to significant shortages and hardship. It came at the end of a protracted period of generally below average rainfall, and the cumulative effect of several seasons of rainfall like this contributed to shortages and also to an economic crisis in Tanzania. So that's one form that rainfall data comes in. Here's another form from May 1884, so 90 years before. And this is a report from a missionary based in Mpwapwa, which is about 75 kilometers to the east of Dodoma and has a very similar rainfall regime. The missionary wrote, "There has scarcely been any rain during the past season. Consequently, there will be a scourge of hunger, for it seems to be all over the country." Now, in displaying these 2 sources of data, I think there are 2 challenges which I'm going to kind of explore and we're going to examine further as we move on in this session. Firstly, where do we get these kinds of data? And I'm going to show you a few examples of that just to get us going. And secondly, how do we directly compare these types of data? E.g., for example, can we say that 1973 or 4 or 1883 to 4 had more or less rainfall in the region around or between Dodoma and Mpwapwa? Can we make direct comparisons between these kinds of data, the qualitative description from 1884 and the statistics from 1974? Or in short, how do you make these 2 different types of data interoperable? And we're going to answer these 2 questions in turn. And to answer the second question, that will include a practical element, which you are going to lead in breakout rooms. Okay. So rainfall data in the Indian Ocean world. Okay, rain gauges. This is the kind of the bread and butter. This is what most people will be familiar with. And you can all gain access to a lot of rain gauge data at the tip of your fingers at the open access Climate Explorer, which I'm going to put over here and show you. Now, some of you maybe, I hope you're all familiar with this, particularly those who came to last year's workshop, which was organized by the University of Sussex. Now, last year we did some monthly reanalysis fields down here. We're going to go a different aspect of the Climate Explorer today. Monthly station data. And for here, you want to click on the Global Historical Climatology Network, or the GHCN, and all. And this is a searchable database of all the kind of readily available rain gauge data that the GHCN has identified. And it is fairly expansive. Now, if we're going to click on this, I'm just going to show you an example of what the data comes in. I'm going to go, just as an example, search India, and then get stations. And here you have a list of all the rain gauges, of which there are 169 stations where rain gauges were had at some point in the past. Each rain gauge, if you see here, has a name, it has coordinates, it has a station code, and it has the years for which there are data. So the Kindia Guinea one, so this is actually in Guinea. This is because obviously searching India, you get Kindia as well. But if you kind of scroll down, you get the ones that are in India. Here you go. And you have data from 1881 to 1984 for Dhubri in India. If you kind of scroll through this, you'll see that there is a lot of data for the 20th century, and some go back to the 19th century. You can see here in Guwahati from 1848. The longest time series we have is actually for Chennai, which is stored as Madras, which you have all the way back to 1813 to 2018. And this is a consistent, this is 206 years of data about rainfall. If you click on Get Data, you can see some visualization. This is the average down here for January to February, sorry, January to December, or if you want it in a slightly different form, July to June. And this is just on monthly, how much the rainfall fell kind of visualized. It's kind of difficult to read. And so therefore I'd kind of urge you instead to click on raw data. And this is the raw data. 1813 in January, 0 millimeters of rainfall. 1817 in April, again, 0 millimeters of rainfall. There are some gaps in the data. Obviously, you can see here, this minus 999.9. That just means there's no data collected in this month. But this is basically a consistent time series of rainfall data for Chennai from 1813 all the way to 2018. And you can, I'd urge you, for whatever region, if you're a historian and you're thinking about these things, I'd urge you to check out the Climate Explorer to see what rain gauge data exists, even if you have not done so already. The Chennai data is somewhat an anomaly in terms of its time depth. 1813, I think that's the earliest, the longest standing rain gauge in the Indian Ocean world that I've found. There might be another one I'd love to, but I'm pretty certain that's the one with the longest time series data. For most of the Indian Ocean world, data doesn't really start becoming abundant until the 1870s. And then for some regions, such as East Africa and Southeast Asia, the data doesn't become abundant until 1900s. So it's limited in terms of how much we have, particularly if we want data from the deeper past. So if we don't have this kind of data, what other kinds of data can we have? Well, firstly, you can get natural proxy data. I think of all the natural proxy data that there is available, the most famous is probably tree rings. And this is the discipline of, to analyze tree rings, the discipline is called dendrochronology. And very broadly speaking, and this changes depending on the type of tree or the species of tree, the thicker and the denser of a ring on the intersection of the thicker and denser the tree ring, the more rainfall fell. And here we go, I've got a kind of an example of this kind of data here taken from Thewell et al. Tree ring reconstructed rainfall variability in Zimbabwe, which was published in 2006. They analyzed 4 trees and analyzed their rings and have therefore reconstructed levels of rainfall from around 1800 to 2000 based on the rings. Now, for the early period, it's a bit sketchy on the base that we only have 1 tree ring to make these inferences. For the late 19th and to the mid 20th century, you have a lot more data, so a lot more certainty there is. But based on kind of these, on this ring width index kind of telling you how wide the tree rings are, they've kind of inferred that there's a generally wet period in the 1820s to 30s, another wet period in the 1890s to 1910s, and then frequently below average rainfall up to the mid 20th century. So that's some natural proxy data, which I think is available for a lot of regions of the Indian Ocean world that I think we can access. We also have another type, recordings of natural phenomena. And here's, I think, is probably the most famous in the English world. This is the records of the annual minimum and maximum of the Nile River in Cairo. Notwithstanding some gaps, there is a continuous record for the maximum level that the Nile reached and the minimum level that it reached every year since 622 AD. Now, these measurements are indicative of rainfall in parts of Eastern Africa. All of this data was collected and standardized by Omar Toussoun in 1925, and this is what the data looks like. Because of the seasonal cycles, the maximum, so that's this half of the page down here, and we have it in meters and centimeters here. The annual maximum is seen as a proxy for rainfall in Ethiopia, and the minimum on this side, and meters and centimeters in here, it is considered a proxy for rainfall in Uganda, although it is imperfect. So these aren't, so like tree rings, these measurements aren't actually measurements of rainfall in and of themselves, but they are measurements of things which might be taken as a proxy of rainfall, measurements from which rainfall, levels of rainfall can be inferred. So far, we've looked at statistical data, quantitative data. Now we're going to get into something, we're going to look at more archival data, and that comes in a variety of forms as well. And this often is qualitative information. And this is the type of source that I, as a historian, am generally most familiar with, as a historian of 19th century East Africa, for which there isn't very much statistical data. We mentioned some of this in, Antonia Moon discussed some of this kind of data in last year's summer school, which is available to watch here for data that's held in the India Office records and related collections in the British Library. And sometimes in these archives, like the ones she drew our attention to, and like in this picture here, we actually have statistical measurements of rainfall and other forms of and other aspects of climate and weather. This is a screenshot of some archival material put together by Charles Thomas Wilson, and these are meteorological observations in Rubaga, which is a hill in Kampala, Uganda. And he's made temperature observations over here. And the one that we're interested in, we've got rainfall, and it tells us how much rainfall fell on a 4-hourly scale during the day, which is very, very precise. Notwithstanding, you probably assume there might be some errors here. Charles Thomas Wilson was very much an amateur. But this is also an exception. Actually, in archival materials, normally you get descriptions, and I've got you 3 descriptions here. Just descriptions of climatic conditions. And here are 3 examples of those kind of descriptions, which are cited actually by members of this partnership. So here's one, taken from the casebook of James McGrigor, which is cited in Adamson Colonial Private Diaries on the potential for reconstructing historical climate in Bombay. And this is published in an edited volume by Benita Damaduran, Anna Winterwappen, and Alan Lester. And describing climatic conditions in June 1880, he wrote, "The monsoon draws near, a very little rain has fallen, there has been much lightning, the sun is hot and sultry, the thermometer for some days 93, and wind variable, though generally south and southwest." Here's another one from Fiona Williamson in my forthcoming edited volume. Quote, "The scarcity of water is now most keenly felt throughout the whole town." And this is describing conditions in 1877 in Singapore. Apologies. And then here, cited in Damaduran et al. In the 1780s, describing from F.C. Danvers, looking at Calcutta. There are reasons to believe that the upper parts of Hindustan had been visited with extraordinary drought during the previous years, In September and October 1783, there was an abnormal cessation of rain and extreme drought. And in the latter month, a terrible famine was reported in all the countries beyond Lahore to Kurumnasa, the western boundary of Bihar. The famine had already been severely felt in all districts toward Delhi. To the northward of Calcutta, the crops upon the ground had been scorched and nearly destroyed. All three of these reports suggest that below average rainfall fell in parts of India in 1800, in Singapore in 1877, and India again in 1783. And often we are reliant on these kinds of descriptions to reconstruct past climates because of the lack of quantitative data, either from rain gauges or from proxy sources, such as tree rings or the levels of rivers. In the case of documents, they can also often add precision to interpretations of proxy data. But how do we make all these data points interoperable? That is, how can we make these descriptions useful to climatologists trying to use past data to make models for the future? Can we use these kinds of descriptions to make a longer time series that includes, for example, rain gauge data? If the answer is yes, then historians and social scientists can provide useful data points that climatologists can use to make more accurate models of climatic behavior in the present and future. The good news is that the answer to this question is actually yes. And the way you do it is through a process of indexing. So what is indexing? Well, there's a summary which was shared with me last year by Dr. Mick Frogley, who is a member of this partnership. And I urge everybody who's interested in this to actually go and read this article. It's David Nash et al. Climate Indices in Historical Climate Reconstructions, a Global State of the Art. And this kind of gives more detail on how historians and climatologists and historical climatologists have indexed their data. Basically, indexing involves converting qualitative information into continuous quantitative proxy data. It's about assigning a number to reflect levels of rainfall based on the description and any other proxy information that you might have. Now, to give more details, I'm going to give you some examples to kind of explain what we mean by this. Now, there are generally three types of index for rainfall that have been used, whether in the Indian Ocean world or elsewhere. These are a 3-point index, a 5-point index, or a 7-point index. So to give you a first example, a 3-point index. And this is basically, this was recently used by Joël Gergis and Lyndon Ashcroft for measuring rainfall variations in southeastern Australia from 1788 to 2008. So this is incorporating a variety of data points and different types of data through an index, because there certainly is no rain gauge data for the late 18th century, which they incorporate into their index, into their time series. And they use a 3-point index. And basically, -1 in the index is a dry year, 0 is a normal year or above average rainfall, and +1 is wet or above average rainfall. And this kind of this kind of index is particularly useful when descriptions in archival documents lack detail. You might think one of the ones I just referred to, the one from Singapore, which just said the scarcity of water is now most keenly felt throughout the whole town. Now, if this is the only data point you have, the only description you have, you might suggest that this data point on its own is suggestive of a -1 classification, i.e. it signifies that this year 1877 was a dry year in Singapore's history. And kind of using this kind of methodology, Gergis and Ashcroft identified 71 wet years, 69 normal years, and 81 dry years in this long time series of data for southeastern Australia. Now, adding more precision, a 5-point classification. And this example comes from George Adamson and David Nash's documentary reconstruction of monsoon variability over Western India from 1781 to 1860. So it's starting at a roughly similar time. And here they classify 5 different points. You'll see again, 0 represents normal, but +1 is above normal, +2 is excess, -1 below normal, and -2 deficient. This requires more detail in your source or a selection of sources allowing you for more certainty. I think if you really push it, you might even argue that that quotation from Singapore, the scarcity of water is now most keenly felt throughout the whole town. If you only had this, perhaps you'd suggest a -2. The source is suggestive, at least, that water is deficient enough that it created hardship. It does suggest not just below normal, but deficiency. Now, to actually adopt this kind of position, I think you'd hope to have more sources to support this assessment. And I wouldn't recommend using a 5-point index if that was the only source that you had. But nevertheless, this is suggestive of that. And if you had other sources, which I will actually kind of make a spoiler here, do exist, you could make this point that it is a -2. So again, so 2 to -2 with 0 representing normal for a 5-point. Now, the 7-point index, of course, requires even more detail. And this was kind of adopted by Sharon Nicholson, Amin K. Desfouli, and Douglas Clotter on a 2-century precipitation data set for the continent of Africa. And they made an annual time series for representing rainfall over the entire continent of Africa from 1800 to 2000. And they kind of used very broadly these definitions, that a -3 would be a climate-driven famine, a -2 would be significantly below average rainfall, -1 would be slightly below average rainfall, 0, again, average levels of rainfall, 1, slightly above average rainfall, 2, significantly above average rainfall, and +3, climate-driven floods. And this example, which this does rely on a lot of qualitative descriptions, but also relies on proxy data as well, such as tree rings. And you can kind of see they divided Africa up into 90 different rainfall regions, and they all have their corresponding number, which is kind of shown along here for each of the regions. And these are the years going up here, and the different colors represent different points on their index. Now you can kind of see in the 1830s all the way up here is suggesting a lot of -3s in regions 10 to about 20. So they're suggesting that there are climate-driven famines in the Sahel region of Africa during the late 1820s to 1830s. Now, you need significantly more detail in the sources to be able to use a 7-point classification. And I think one of those sources that I pointed you towards suggests that actually you could use a 7-point classification for that. That is this one here, this description, which discussed the abnormal succession of rain and extreme drought, and in the latter month, the terrible famine, which suggests a -3 categorization. It suggests a climate-driven famine. Now, more sources will help to verify this, but broadly speaking, I think this is what you the sources are at least suggestive that this is where you go for. It explicitly suggests that drought was linked to the famine, and you might therefore assign a -3 grade on a 7-point wetness index. And other sources, of course, would help to support, or you'd hopefully find some natural sources or more reports like this to kind of be more precise about, or more happier with your kind of classification of -3 there. But this is at least suggestive that a -3 would be assigned. So, task then is I want you to index some reports. I want you to index some qualitative descriptions of rainfall in the 1870s to 80s in East Africa. All these places that I'm going to give you are in present-day Tanzania. But before I give you some more precise instructions, there are some more details about this region and time period that I think are particularly interesting. This idea of using a 7-point index for this makes it interoperable with Nicholson, Desfouli, and Clotter's index, which is an annual index for all of Africa. But this index does have its limitations. The rainy season in inland Tanzania lasts from November to April. Thus, their annual index does not accurately depict like a seasonal variation. If you don't know how wet a particular rainy season was, because they're splitting each rainy season up. By contrast, what I want you to do is to collect monthly data and assign a number between -3 and +3 for each month of the rainy season from November to April. And this is actually building on Nicholson's ideas. Nicholson wrote in another publication, quote, "For Africa, much more documentary information exists than has ever been exploited. Most of it, however, is not readily available to the non-specialist. Retrieval from historical archives and general evaluation of material are generally best done by a historian," or I'm going to extend that to all social scientists. And that's basically what she's calling for. She's calling for social scientists, historians to add more precision to her kind of index. And basically here, what I'm going to do is I'm going to provide you with some archival materials to fill this kind of lacuna, respond to this call, providing a higher temporal resolution than she has already, and therefore giving more precision to changing levels of rainfall over time. Okay, so I'm going to give you breakout rooms. There are going to be 3 groups. I think that's going to be the best with 17 participants. I know we'll do 3 groups. Group 1, we're going to make a 7-point index for Mpwapwa, which is here in Eastern Ugogo. Group 2, a 7-point index for Tabora, which is in Unyamwezi. And group 3, make a 7-point index for the southern shores of Lake Victoria, which are broadly focused on Wanza. And there are some additional questions for you to work through as well. You'll also note that on this map, I've not just marked these stars where you're going to be doing the rain gauge data. I've also marked 3 nearby rain gauges. One in Kampala, which has data from 1878 to 86, Mombasa from 1875 to 81, and Zanzibar town for 1874 to 1881. And to kind of get this going, I've already indexed this data using a 7-point index. If it was less than 70%, if the reading was less than 75% of average, then I assigned it -3, 75 to 85%, I assigned it -1, and so forth, all the way up to +3, which is more than 125% of average. Now, here I have put it into a time lapse using QGIS. And here you can see my key. When I have a reading for -3, I assign it a very dark red. When it's -2, slightly lighter red. -1, kind of a peach. 0 is close to white. 1 is light blue. 2, slightly darker blue. And 3 is very much a deeper blue. And here's the time lapse. You can see that this current frame, what we're looking at is that we have the rainfall for January 1874. And we have and because that's the Zanzibar town is the only place that we have data for rain gauge, that's the only thing we can see. And in January 1874, the rain gauge suggests that there was a severe deficiency of rainfall. That if it lasted long enough, that there could have been a famine, a drought-driven famine. Now, if we keep on pushing this along, so now we're moving along. We're now looking at May, June, July, August, and you can see that the level of rainfall changes over time. So if we pause it here, we're now looking at January 1875. In Zanzibar town, it's suggesting above average rainfall, but in Mombasa, it's suggesting basically normal levels of rainfall. And now if we keep going again, you can see there's some differences, particularly in the dry months when there isn't any rainfall hardly any rainfall falling at all. But here we have February 1876. We're looking at deficient rainfall in coastal and island regions of East Africa. You can see February 1876 here. Now, if we keep pushing this along, we'll do it until we get to some data from Kampala, which is going to come up very shortly when we start in 1878. So we're in 1877 now. There's just a couple of data points in 1878 for compiler. It's going to start in April. Here we go. We're looking at some very, so divergence between inland and coastal regions in June 1878, but not very much rainfall falls then anyway, so it's not particularly serious. Now moving into 1879, we start getting more continuous data for all of them. And October 1879, or if we move it across one, there we go. So November 1879, we're looking at a region-wide drought at the beginning of the beginning of the rainy season. So November marks the beginning of the rainy season, and we can see that everywhere is deficient rainfall, but particularly in inland zones. Now, this is all kind of well and good, but we're only providing data for these 3 places here. What would be really useful is does this correspond to what's going on here at Mpwapwa, Tabora, and Mwanza? Now, we don't know if we just look at rainfall data, because it just doesn't exist. So this is why archives are so important. You need to read the descriptions and assign them a number for each month based on the same, based on using the same scale. Now, how do you do this? Well, you should have seen in the emails that we've circulated that I've given you some exercises. And if you haven't read, there's no problem if you haven't read them already. So this is the sheet for Mpwapwa in Eastern Ugogo. So that's down here. I've given you a description of the location. I've told you, reiterated, that the rainy season lasts from November to April. So I want monthly rainfall data for each of the months in the rainy season. I've given you the scale. And basically your task is to fill in all these, use these descriptions that I've given you here to fill in all these tables as best you can, suggesting how much rainfall fell on this scale from -3 to severe drought to +3 to floods in all of these months. Now, this is actually a very difficult task, and I want to read this out to you because I want to really stress it. You're going to encounter several methodological challenges as you go through this exercise. A lot of the numbers you input will be from evidence that is more suggestive than definitive. But by visualizing the data in the final session of today's workshop, which is what we're going to do at the end after Professor Lowe's presentation, after Professor Lowe's session, we might get a better picture of whether your interpretation of the often sparse archival material stands up. For example, if the material from a particular month suggests a -1 reading, does this correspond to similar readings of the other archival data, as well as to the rain gauges in Kampala, Mombasa, and Zanzibar? And broadly speaking, we should expect some correlation, as each location I've just mentioned is subject to the same climatic forces and the same, generally speaking, the same seasonal schedule as well. Thus, and this is kind of difficult, this will be difficult just with the sources that you have, I really must insist that no matter how inclusive the archive material appears, you should write an index value for each month. And then we can test in the final session whether your interpretation is supported by the interpretations of your peers for collecting the for indexing the data for the other locations. The data from each data set, so that's the rain gauge from the 3 different exercises, should to a fairly large degree support each other. And so if it does not, this will help us to weed out some erroneous results or reports or interpretations of the archive. Additionally, to help you with this exercise, because I think it is quite difficult, I provide you with hints about the data for each session. And I'll give you some questions to think about as you go through. How are you deciding what represents significant? For example, the difference between -1 and -2 and 1 and 2 and other distinctions. How are you accounting for months of missing data? Because there are several months of missing data, but there are reports that kind of refer back to earlier times. And what kind of sources are these documents taken from? In what ways are they useful or not useful for reconstructing levels of rainfall? Answering these questions are then going to form the basis of a discussion at the end of this session. But once you filled out the tables, and so I want you to do 1 per group, please send the document to me. There's my email address. And then I'm going to use your indexes and I'm going to input them on this map. And then we're going to see a time lapse that incorporates both the rain gauge data and your interpretation of the archival sources as well. All right, is there any questions at this stage? All right, I think the next task is to put everyone into breakout rooms. Have you got the right screen? Hold on. You got the PowerPoint? Is the PowerPoint coming up? Someone give me a thumbs up.
Yeah, the PowerPoint's there.
Excellent, thank you. All right. We're fine. Okay, so to do this data visualization, I'm using a program called QGIS. This is open access and open source software, so everybody here has access to it. I actually taught myself how to use this using online tutorials. Basically, because it's open source and open access, it means that everybody posts their questions online and everybody responds to it. It's a proper collective, really, basically. This also means that it's not very complicated. Every answer you could possibly need to get is online. It means you can do it if you want it to do it. But there are certainly also more complex things you can do with similar, with more power, higher powered software. For example, the stuff with Esri, which produces ArcGIS, which is subscription based. My university has subscription to it. I imagine a lot of yours do too, but I don't think it's universal. And as the program moves on, and as the project goes on, the data will be stored in Esri. It looks like it's going to be stored in an Esri database, so it looks like we're going to be moving towards that. But that's kind of beside the point. I wanted to kind of emphasize here that you can do this too if you wanted to. If you're interested, I'd be glad to actually walk you through this process of how I did this at some point, some other day. I am no GIS expert, though. So it'd be less of a workshop, but more of a kind of a meeting where you can discuss and collaborate on how to use it, and also the methodological challenges and pitfalls of it as well. So I asked you to collect data for the 1870s and 80s in Eastern Africa. Actually, all the regions are either in 38 or all the places are either in 38 or 32 on Nicholson's region. And I've highlighted all the East African regions here. You will notice if you go to the 1870s and 1880s and the highlighted ones, you've got some good levels of rainfall in the late 1870s. It looks like on an annual scale, but then moving to a lot of droughts in the 1880s. This is what they suggest on the annual January to December kind of time series. Now let's see what we come up with, what you came up with. Here we go. So we're back to this again. This is QGIS. Again, here's your scale. -3 is the deep red. +3 is yeah, pretty deep blue, and everything in between. Starting in 1874, which is where the rain gauge data starts, and then we're going to see your indexes pop up as we go along as well. So 1874. This is the rain gauge data for Zanzibar. This is the only data that we have for 1874. We're going to come up to, so in September, October, November, December 74. Now 75, we've got some data coming in from Mombasa as well on the East African coast, on the mainland coast. So we're still just using the rain gauge data at the moment. I think the first data that's going to come up is, I can't remember, if it's Mwanza or Mpwapwa. We'll come up with that in a second. Now in 1876, and here we go, Mwanza. So here we go. So we're looking at January 1877. We're looking at the coastal areas and island areas saying drought. We're looking like a drought on inland as well. It's like it's a region-wide drought or deficient rainfall in January 1877. From what you suggest, there's a fairly high degree of correlation between what the rain gauge is telling for the coast and island regions and what's coming for the inland. And I think that's particularly interesting. Here we go now for 1877. We've got a lot of blues and normal rainfalls. The middle months of 1878 aren't particularly interesting. Now we're moving to the 1879. We'll pause it in the latter months of 1879. So I think that's a particularly interesting time. 1879 November. All right, region-wide drought again in November 1879. This is coming through in all three rain gauges that we have data for. I'm also getting it in Mpwapwa as well from your data. So it looks like this drought, which is suggested in the rain gauge, actually comes into what is now Tanzania 2, just from the archival sources. And again, this kind of continues with similar patterns between coast and Mpwapwa. Now we move into 1880. I think we've got a little gap here between until we get to the next set of data, which I think we're going to get some for 1882 to 3 for Tabora. It's now we're into 1882. We're going to get to in April and now May. We'll keep it going until November again. Here we go. So now we've got, now our rain gauges have stopped on the coast, but we've got a rain gauge in Kampala, and we've got the archival sources from Tabora that you indexed. And there is, again, a fair amount of correlation between the two, suggesting region-wide patterns. And here we go. Now we're in the 1883 drought. And this is the one that everyone indexed. And the index suggested it wasn't quite so severe on the southern coast of Lake Victoria, but everywhere else, we've got the -3 for a famine level drought for pretty much the whole period, except for one month in Kampala, apparently, which was significant. That was significantly more. Now, that 1 month was February, maybe, and I'd be willing to bet at this point that maybe this is where the archival data is a little bit weak. We didn't have very many reports from February itself, and you kind of lack the resolution to be able to be absolutely certain. So maybe there's a little bit of discrepancy there that maybe we need to revise moving forwards. Now we're still in 1884. Now we're going to go to 1880. The next stage will be looking at 1885 to 6 season. Okay, so we're looking in November around Lake Victoria. We're looking at a region-wide drought around Lake Victoria from the rain gauge and the archival data. At the beginning, the late onset rains. A late onset of rains. Kampala looks a little bit wetter than Mwanza, but again, that might be because there's a shortage of data. Now, here we get to a point where we've got no rain gauges at all, and you've only got the Tabora data from the archives, and this is all we rely on. What I want to say actually here that I think is particularly interesting about this, we're going to get a bit more Tabora again for 1886 to 7, 1887 to 1888. Significantly less has been written on this drought than on earlier ones. And I think that is partly a reflection of the fact we know less about it, just in terms of its statistical severity. Now, Kampala, from archival sources, and I didn't ask you to look at them, actually suggests that there's a significant drought on the northern shores of Lake Victoria as well, which contributed to major shortages and to an outbreak of bubonic plague, believe it or not. And so there is more archival sources to draw parallels across there too. But anyway, I think that was a particularly interesting exercise. I think we've got from that, if we spent a longer time integrating it and studying it in more depth and looking at it alongside the actual reports, we could get a better flavor of the region-wide scale of rainfall patterns than we get with just rain gauges. And I think that was particularly interesting. I think you'd revise a couple of the archival sources based on the rain gauge data as well, or maybe the rain gauge data will tell you to look for maybe different levels of rainfall, and maybe we'll revise a little bit, but just on their own. And in terms of the interdisciplinary practice of climate history, you'd expect to do that as well. But just on their own, there's some interesting parallels, interesting patterns going on there, which I think can really be shown by making diverse data interoperable, which is what we did first, and then also by visualizing it, just by doing that. As I said, I'd be happy to kind of try and work with you to actually do that. Now, there are a couple of other things I just want to draw your attention to before we go. The size of these boxes is that's not a coincidence. I made these boxes 1 degree by 1 degree. These are, and I could have made them any size, maybe make them that size because it makes it easy to see. But I made them 1 degree by 1 degree, so 111 by 111 square kilometers. Now, the reason I did that, not just because you can see them like that, but you also notice from them that they're not absolutely centered around they're not absolutely centered. Like Kampala's right in the corner of it, and Tabora is pretty much centered, but they're all kind of on the edge. Now, why did I do that? What was my thinking on that? Well, there's one particular reason, and I want to draw this is just for those of you who were here who were at the Sussex Summer School last year. back to the Climate Explorer. You actually did some work on this. Monthly reanalysis fields, the 20th century reanalysis, the precipitation data, select field. Now here, if you put in latitude, and this is the latitude and longitude for basically 1 degree or 1 degree area, that's the highest resolution as it gets. So actually where we're lacking lots and lots of data, there is a climate reconstruction that actually might be able to fill in the gaps eventually. Now I've done a few preliminary tests and to suggest that you actually don't do this yet. There are some discrepancies between what the reanalysis and basically the reconstruction says and what is actually seen on the ground by rain gauges and archival sources. But there's an opportunity here to keep on working on historical climatology, and hopefully climatologists will keep on working on this as well. And the data that we provide them as historians or social scientists can perhaps help them to improve their models. And therefore we can actually, even though we don't have archival sources or rain gauge sources or any other kind of proxy data like tree rings, there are ways to fill in the gaps here too from a spatial standpoint. If that's kind of lost you a little bit, and maybe it has, I urge you to look at the speaker series, so not the speaker series, the summer school, another S illustration, the summer school for last year from the University of Sussex, and I provided one of the links to it, on my PowerPoint. So please go ahead and do that and think about maybe having out the gaps with some basically reconstructive work. Now, the final thing as well, and this is kind of a wider hope for the project, is that, as I kind of said, like you will just kind of incredibly, despite not East Africa, 19th century East Africa it's my specialism. I don't think it's any of your specialisms yourselves, but you actually did an incredible amount of work here that actually produced very usable data that's interoperable. Now, I hope that some of you are interested in this, just as a methodology. A couple of you mentioned that you were, and that you'll produce your own data sets along these lines and also visualize them as well. And also submit your data sets for the Appraising Risk Partnership. And therefore, eventually, the idea was to have data sets like this visualized for basically as far back as we can go, as far back as possible. And therefore we can then, if we're able to do that, integrating archival sources which have yet to be fully exploited, we'll be able to probably, I hope, we'll be able to shed new light on the changing patterns of the Indian Ocean monsoon system and how it's acted under different conditions and over different years, which will be absolutely integral absolutely vital for modeling the future effects of global warming in the Indian Ocean world. All right, I'm going to call it there.